Okay, I have a new model showing the Earth. And so this is a update of my Earth's magnetic field source video. And this compass is pointing to magnetic north. I'm here at 40 degrees north and about 111 degrees west latitude. And so you see both these needles are pointing pretty much north. I mean, magnetic north here in this location. But I have a belief, a theory that a magnet in the core of a ball Earth or up here, a big, huge magnet, doesn't make any sense, because if you look at the field intensity, you'll see like 60,000 microteslas here, or maybe nanoteslas, and like 40,000 here, and at the extremities, it'd be like 20,000. Well, that's a factor of 3. And the inverse square law of magnetism and light should be that this should be like 100 times or 1,000 times stronger with this distance. At Barrow, Alaska, they should be having forks moved off their plates, and here you would feel nothing because it attenuates that much over. This would be about 12,000 miles. And so, you can't transmit a beam of light 12,000 miles and have the inverse square law still be able to pick it up here. Some radio waves, yeah, they do, but it's pretty hard. You got to put out quite a bit of power. But a magnet? No. Anything that could be run a compass down here would be pulling metal objects up here. So that doesn't make any sense. Even if I put a huge neodymium right here, by the time you're out here, you might feel it and you might not. But a half a mile away, nah, not going to happen. So now I'm going to override the Earth's natural magnetic field, because I've put coiled wires, a spiral of copper wires coming out from here, because if you take any conductor in a ring, it doesn't matter if it's a ball or it's flat or whatever, a conductive field here, and you put a heat source over here, and then this is cool, you create an electrical current, and that creates a magnetic field. So you see both things. This particular area is a little bit weak. The deviation is quite high here, but you can see here, this is the magnetic north. The center point of the sidereal spin is not aligned exactly with the magnetic north, which is more like about here. And so that's the way I've wound this thing. So there you see it. This thing really wobbles a lot, but you can see it does it there. So that's what I believe is powering our compasses. Is right below your feet. You've got water tables. That water is in contact with minerals, and therefore it's a good conductor. It's not distilled water. And we have a heat source called the sun, which moves over the surface. And whenever the sun is here and it has a hot spot right underneath it, there's a lot of heat right here, and there's no sun over there. If there happens to be a full moon, that's even more cooling. But at any rate, you've always got heat on one side and cool on the other side, and it goes around and around, creating a continuous electrical current. And there are deviations, because the whatever it is that's flowing could change. Now see here, this deviation is way off, because I've put wires in there crazy sideways to indicate that 70 degrees deviation down there, about right here in tip of the Antarctica comes up by Cape of Cape Horn here. There you have it. Now, temporary magnetic field or local magnetic field off. And it takes a while for the currents to actually die down, but there you go. Oh, this guy was already pointed north there. So there's actually some capacitance in coils. So that even though I turn it on, and now it's working, this guy's really swinging around a lot. But you see here, this is working. I turn it off, watch, it takes about a second or so. It didn't take any time to. Yeah. Okay, there it is. Magnetic currents, electrical currents underneath the surface of the Earth. You know, it could be just like 10 feet down, 100 feet down, whatever. That's what's producing our Earth's electrical magnetic field for the compasses. Thank you.